Hi folks, welcome back to Physics with Captain Rod. The purpose of this video is to introduce you to a very important concept in physics called work. Let me write down how it's calculated and then I'm going to go through some examples. So in physics, work is force times distance. So the units of work would be the Newton meter in the SI system or the pound foot in the English system. There's some important details here though. Let's talk about the distance first. The distance is not the distance between 2 points, it's the displacement of the particle of which the force is applied. So it's important to know that there has to be a displacement. Something needs to move for work to be done. Second, when we do the calculation, work is force times distance. The force has to be parallel to the distance. That's really important. Forces that make a right angle to the displacement aren't doing work. I'm going to go through some examples here. We're going to talk conceptually how work is calculated. So looking over here on the left, we got this guy lifting this dumbbell. Now for this example, imagine he lifts that dumbbell from position 1 to position 2, and imagine he lifts it in a fairly slow manner. He's not accelerating it. A free body of the dumbbell might look something like this. The person is applying a force here and maybe at the back neck area, and then another one here. I'm just kind of grouping those into one force up. If the person lifts the dumbbell slowly so that there's no acceleration, the net force on the dumbbell is 0. So we can write out, all right, sum of all forces would equal 0. And that means that this force minus mg would equal 0. So the force that the person applies is equal to mg, the weight of the dumbbell. That's not too surprising. Right? The work done is going to depend on the height, the height difference between 1 and 2. So I'm going to give this a name here. I'm going to call this distance h. If the person lifts this from 1 to 2, the work done would be the force that they apply, which I'm just going to call F, times the distance h. Now, work can be positive or negative depending on the relationship between the force and the velocity vector. Here's how you determine that. If the force vector is in the same direction as the velocity, I'm putting symbols over here to denote these are vector quantities. If the force vector is in the same direction as the velocity, then the work is positive, or we would say mathematically it's greater than 0. When the force is in the opposite direction as the velocity, then the work is negative. Right? So in this example, if the person applies this force F as this thing goes from 1 to 2, the work done would be positive F times h. And since F is equal to mg, we could write that positive mgh. And again, I'm going to put a plus sign here to denote that work would be positive. If the person, however, lowers this from 2 back to 1, again slowly, there's no acceleration, the free body doesn't change. The force that the person applies on the dumbbell is still up. So if the dumbbell moves from 2 to 1, the work done is still force times distance h, but it's negative now because the force vector is in the opposite direction of the velocity. Right? Again, if this thing's moving from 2 to 1, the velocity vector for this particle would be down. When the force is in the opposite direction of the velocity, work done negative. So if we wanted to, we could write that term minus mgh. Right? Let's take a look at this example here. If this person starts pushing this box, and imagine that they push this box a distance d to the following location. Right, so imagine that this person, oops, not sure if that's quite going to cut it. Try that again. Imagine this person moves this box over here. And again, I'm going to give this distance a name. We'll call it d. And we're going to go through some work calculations. I just need to clear off some space here. All right. First thing we're going to do when we talk about work, we're going to draw a free body of the box, and then from that free body talk about the different forces doing work. Right, so a free body of this box might look something like this. I'm going to use my little straight edge feature for this because I like nice straight force vectors. This person is going to push on this box. It's going to slide along this path. Now we're going to imagine this example that it's moving at a nice constant speed. The force vector that they apply would point this way. The gravitational force on this would be down. Here we have a surface in contact. That's going to give us another force that in physics we would typically call normal force. That would be up. And here we have another surface in contact. That's going to give us a potential for a frictional force, which in this example, if there is a frictional force, it would be to the left. If this thing is moving at constant velocity, we would know these two forces are equal. Now, when I kind of look at all four of these forces here and we start thinking about work, and I'm not going to worry much about magnitudes, or I'm not going to worry about actual numerical calculations. I just want to talk about how would the work be calculated. So if I consider all forces here, we're going to take this one first. The work done by that person, I'll put the work done by the applied force F here, would equal the force that they apply times the distance, and that work would be positive. The normal force. The work done by the normal force would be 0 because the normal force is making a right angle to the velocity, or the velocity vector. A very important sentence I always make everybody remember for work. Only forces in the direction of motion do work. So in this example, this box is moving this way. Only forces parallel to that path are doing work. So this one's doing work. The frictional force, it turns out, is doing work, but the normal is not because it makes a right angle. Work done by the gravitational force, the work done by mg here, 0 for the same reason. The gravitational force makes a right angle to the displacement. The work done by the frictional force is going to equal whatever the frictional force is times the distance, and the work done by the frictional force would be a negative number. The reason? The velocity of the box is to the right, the frictional force is to the left. So when we're calculating work, work is force times distance. Only forces in the direction of motion do work. So in this example, as this box moves to the right, the normal force is not doing work and the gravitational force not doing work. That's going to be important for us later on, identifying when forces are not doing work. This force is doing positive work. This force is doing negative work. And I think I'm going to leave this video off right here and do the kind of deeper, more conceptual stuff here later. That's enough for now. The important part of this video is 1, how is work calculated, force times distance. 2, recognizing only forces pardon me, in the direction of motion do work. So in this example, that would be these two. Forces that make a right angle don't do any work. Third, the work is positive when the force is in the direction of the velocity. So in this example, this box we were imagining, it was moving this way. So this force is doing positive work. This force would be doing negative work. And that's good enough for this video. Everybody have a great day.